There we go. That should be everything set up that we need. So this is the problem solving session for November 13th. There was one post, I'm just refreshing it to make sure that's still true. Okay. One post to the forum asking about 3 different questions. Problem 4 on homework 17, and then problems 5 and 6 on homework 18. So I'm gonna start with homework 17, problem 4. And for this one, we're given capital F equal to yz squared I hat plus xz squared j hat plus 2xyz k hat. Yz squared, xz squared, 2xyz. Okay, cool. And we're asked to show that this is conservative by finding a scalar potential function f. So we're trying to find little f so that big F that we're given is the gradient of that potential function. That's what you're trying to do every time you hear show it's conservative, find a potential function, or any of these line integral problems we do using this property. So our approach here is going to be to integrate the x component with respect to x, y component with respect to y, and z component with respect to z, and then hold on to all the unique terms that we find. So that's going to look like computing these 3 integrals right here. That comes from the fact that I want the derivatives of little f to match big F. So if I'm given big F, I go ahead and integrate it so that I end up with little f. I'm skipping some steps here that I would have shown in the lecture videos, but this is kind of how you sit down and do the problem itself. So, integrating yz squared with respect to x. Remember that yz squared is a constant as far as x is concerned, so I could go ahead and pull that out of the integral, and then I would just be left with the integral of dx, which just gives me x out of it. But there's some unknown constant that could potentially depend on y and z that I wouldn't see if I integrate just the I component of the gradient here. Same idea with integrating xz squared with respect to y. X and z are a constant as far as y is concerned. So I could pull that out front and just be left with dy inside the integral. So I would just get xz squared times y, plus there might be some constant that I don't know what it is that only has x and z in it that I couldn't recover from integrating the jth component. And then for the third integral, 2xy is, actually, make it a little easier on myself, xy is a constant as far as z is concerned. So is 2, but it's nicer for me if I leave it inside the integral. So I'm just integrating 2z with respect to z. But the integral of 2z is just going to be z squared times that xy. And again, there might be some constant that depends on only x and y that wouldn't show up from integrating the kth component with respect to z. So when you're doing your own problems, you don't have to do this pulling out of the integral if you don't want to. I just did it to kind of show why I'm skipping yz squared, xz squared, and xy, because those things are constants with respect to the variable we're currently integrating. If we look at these 3, I'm going to rearrange them so they all are kind of in the same order, so it's easier to see that yz squared x, I'm going to reorder like alphabetically as xyz squared. Same in the next, xz squared y is just xyz squared. And xyz squared in the last one was already the order I wanted, so I'll leave it that way. So now it's easier for me to see that these three things I got out of my integrals are all exactly the same. The reason that matters is because my approach is always to say, okay, f is going to be made up of everything that I found from the first integral. But then when I get down to the second integral, I cross out any terms I've already found before, which was that xyz squared. And then if there were other terms, I would go ahead and add them here, but there are no other terms, so I don't have anything to add. Same with the third, that xyz squared I already found is already in my function f, so I don't add it again. I don't get like f is 3 of those repeated or something like that. And we can also see now that the C1, C2, C3 that we were carefully marking might exist actually doesn't. So I didn't find anything when I integrated here that would have been contained in C1 or C2. Same with the other equations for the other constants. So at this point, the web work problem is done. You would just put in your answer. I guess I'm going to make sure that's right. Cool, it is. But if this was an exam and you couldn't get that instant feedback from web work, but you wanted to check if it was right, you could go ahead and compute your gradient vector. Using like the definition of a gradient. Maybe you don't like this partial notation, maybe you do like fx, fy, fc, whatever your preference is. But the derivative with respect to x of xyz squared is just yz squared. The derivative with respect to y of xyz squared is just xz squared. We're kind of seeing that yz squared is a constant with respect to x, and xz squared is a constant with respect to y. And then the derivative with respect to z of xyz squared, xy is a constant with respect to z. And then the derivative of z squared is just 2z. And just like we wanted, this is that capital F that we started with. If you had added them all up, sort of forgetting to cancel out the terms that you already found, then when you calculate this grad F, you would actually get like there's an extra 3 hanging around. You would have 3yz squared, 3xz squared, 6xyz. And that would not be the capital F that we wanted to find. So you always got to be careful to skip those terms that you already found. But if you accidentally hold on to too many, you can always check if you did it right by computing this gradient. So that was homework 17, problem 4. Now we're on to homework 18, problems 5 and 6. So for problem 5, we're asked to compute this integral. We're told that it's independent of path, and we want to evaluate the integral when the path is given parametrically by that thing right there. So let's write all that out. 3x squared y plus y squared dx plus x cubed plus 2xy dy. C is given by r equal to t I hat t squared plus t minus 2 j hat. And there is no k component. This is just an integral with respect to x and y, so there's nothing else to do there. For 0 less than or equal to t less than or equal to 2. So just a note before I jump into this and do it the way I want to do it. If you decided that you wanted to parameterize and solve the problem that way, you could go ahead and do that. Parameterization is like a nice hammer that'll hit a lot of different line integral problems. So kind of if you have a problem that's a line integral and you don't know what else to do, go ahead and try parameterization because it usually works. But it's a lot of work, especially if you're not given the parameterization to start, and so there are a lot of the time easier ways to solve a line integral. And in this case, the hint that we can solve it a different way is that we're told it's independent of path. Independent of path means conservative, means there's a potential function. So that web work telling us it's independent of path is telling us we can use the fundamental theorem of calculus for line integrals. We can use that potential function approach where we just evaluate at the endpoints. If you weren't told it's independent of path, maybe by looking at these functions you would say they have some terms that are kind of similar to each other. There might be a potential function here. That's a little bit harder to spot, but once you do a lot of these problems, it does get easier. So I'm going to take the approach of finding the potential function and using the FTC, but you could do this however you wanted as long as you got the answer at the end. Oops. And so that's that idea that if capital F is the gradient of little f, then we evaluate little f at the endpoints and take the difference to evaluate this integral. It's antiderivatives for line integrals. So in this case, f, big F, is 3x squared y plus y squared, x cubed plus 2xy. I just read that off my dx and dy components here. And to start this, I need to find the little f so that big F is a gradient of that potential function. It's going to be exactly the same approach we took to find little f here. It's just now after we find that little f, we actually use it to solve this problem. So I'm going to try integrating the x component or the I component with respect to x, and I'm going to try integrating the j component or the y component with respect to y. And I'm going to see what I get out of it. So the integral of 3x squared y with respect to x, that 3x squared becomes an x cubed, and then y is a constant as far as x is concerned, so it just kind of stays in there. And then the integral of y squared with respect to x, y squared is a constant as far as x is concerned, so it stays where it is, but then integrating with respect to x gives us an x multiplied by that, quote, constant. And there might be some unknown constant here that depends only on y that we wouldn't see when we're trying to integrate the derivative of x against x. We're going to repeat the same thing for the second component. So the integral of x cubed with respect to y. X cubed is a constant as far as y is concerned, so it's going to stay there. But then integrating with respect to y gives us a y multiplied by that constant. And then the integral of 2xy with respect to y, the integral of 2y is going to be that y squared. And then x was a constant as far as y was concerned, so it stayed there the whole time. Sort of thinking about this as x times 2y. And there might be some constant function of x that wouldn't show up when, oh, what did I do? It's weird because the screen on my computer, or my tablet, doesn't look like that. so that's no good. Okay, now it looks the same. Wait, but did all my work go away? Oh no. That's from a different session. Okay. Sorry about this, everyone. Let me write this out real quick. I don't know how that happened. This is gonna go faster this time because I don't have to explain everything. But it's gonna look less neat. I was really proud of that layout so far. So far I'd integrated those things and I got x cubed y plus y squared x plus c1 of y, or x cubed y plus, I think I wrote it xy squared plus c2 of x. So this is the point we had gotten to. And then I'm just going to go ahead and rearrange this one right now. Xy squared is the same as y squared x. I just want to make it clear that those two terms are actually the same, so it's easier to not accidentally double count that. So I'm going to start by looking at the result of my first integral, and I'm going to grab all the terms that I see and say that those make up my little f. And then I'm going to go through my second integral, and I'm going to cross out anything that I've already found. So I already found that x cubed y, and I already found that y squared x. So there's nothing new to add to the function. So I think that this is the little f that's going to be used in my fundamental theorem of calculus. If I wanted to be extra careful, I could go ahead and check grad f. When I take derivatives with respect to x, I'm going to get 3x squared y plus y squared. And then taking derivatives with respect to y, I'm going to get x cubed plus 2yx. And you can see that that matches the terms that I had inside that line integral. So it looks like this approach worked. And the reason why I do that is because if you have a random line integral problem and you think that you can solve it using the fundamental theorem of calculus, but actually these terms were not for a conservative vector field, then this check right here would kind of show you, no, that potential function doesn't work. This is not an appropriate approach. So just, you know, something to look out for. But I know this f is good, and so I want to do, and I actually can't remember if I called p the initial or final, so I'm going to do writing out like this. I want to evaluate f at the end point and subtract f at the initial point. So looking at C the way it was given to me, it's a little bit hard to tell what those initial and final points are. I know that I start at t equals 0, and I know I end at t equal 2, so that's something. And then the only part I haven't used yet is this parameterization for C. And remember, when we create parameterizations, we're putting like the x values here and the y values here. So if I plug in my t to this parameterization, I'm going to get the x and y points that corresponded to starting at t equals 0 and starting at t equals 2. So from the first component, x is equal to t, and when t is 0, that's going to give me 0. And when I get to t equals 2, x being t is going to give me 2. looking at the second component, y is t squared plus t minus 2. So when I plug in 0, that's going to give me minus 2. And when I plug in t equals 2, that's going to give me 4. Because 2 squared is 4, then I add 2 and subtract 2. So my initial point was 0 minus 2. And my final point was 2, 4. And so now all I have to do is take those points and plug them into the little f that I found. So my f was x cubed y plus y squared x. So everywhere I see an x, for the final point I'm going to replace with 2. So I've got 2 cubed, and my y at that final point is 4. And then I've got 4 squared cubed 2. So that's my end point. And then at the beginning, x was 0 and y was minus 2. So I'm going to get like 0 cubed times minus 2 plus minus 2 squared times 0. That whole thing is going to be 0 though. So 2 times 2 is 4 times 2 is 8 times 4, and 4 times 4 is 16 times 2 minus that whole thing is 0. So that's 32 plus 32 is 64. So I think my answer is 64. And we're going to see if I was able to do arithmetic. I was. The answer is correct. So I got this answer using the FTC, but if you wanted extra practice, you could go ahead and do it using parameterization, and you should get the same answer out of it. So that's problem 5. And then the last request was for problem 6 on homework 18. So that's this one right here. We're given a vector field, we're told it's conservative, we're told to find a scalar potential f and evaluate the line integral over any path that connects A and B. So this is again a line integral problem, but in this case they're not even giving us the option of parameterization. They're just saying do fundamental theorem of calculus. If you wanted to parameterize this curve, you would have to invent the path that connects those 2 points and then proceed. So my f is 2xz cubed minus e to the minus xy y sine of z minus x e to the minus xy sine of z 3x squared z squared plus e to the minus xy cosine of z. So what's nice is this is going to be an example where we don't get exactly the same thing out of the 3 integrals, because we've got this one term that only has x's and z's in it, so we're going to see how it doesn't show up when we integrate with respect to y. What's not nice is that we have to integrate an exponential with a negative in it, and that's going to throw everyone off when they're doing this problem. And then I guess kind of to show you what they're asking you to do here, we're in 3 space, sorry, 1, 0, minus 1, that's A, and then 0, minus 1, 1, that's B. Sorry if that's kind of hard to see. That's like down here, and that's like that. And they're saying evaluate the line integral for any path that connects these 2 points. So it could be this path, it could be this path. And any path you take, it's going to give you the same answer because this vector field they tell you is conservative. That means it's path independent. If you wanted to parameterize this problem and solve it that way, you would have to draw that path you want. I recommend the straight line, parameterize that line, and then apply the parameterization approach. That's a lot of extra work, but if you were stuck on an exam and couldn't remember how to find a potential function, and this was a free response question and not, or I guess if this was a multiple choice and I'm not checking your work to actually see if you did it the way that you're supposed to, then you would want to do anything that gets you the answer, and that's parameterization. But to solve this using a potential function, we're going to do that thing where we integrate the I component with respect to x, the j component with respect to y, and the k component with respect, oops, I forgot my integral there, k component with respect to z. And I'm going to go ahead and erase that picture and move everything over to the side to give myself space for those integrals, because that picture is really not going to do anything for us the way that we're solving this problem. It was just to illustrate. Okay, there we go. And then I forgot to write my dz right there. So, I was looking for my phone so I could Google how to integrate sine and cosine, because I always forget which one has the negative. But my phone is dead, so I'm going to have to do it here. You all will see the shame of me having to Google integral, or yeah. So the integral of cosine is sine, so we're not going to throw a negative there. If you've ever asked me that question in class, I've told you that I have to Google it, but now everyone who watches this video, all 5 of you, if you hadn't heard that yet, will now know that as well. Okay, so proceeding with the integration, first the integral of 2x z cubed with respect to x. Z cubed is a constant as far as x is concerned, so nothing happens to it. And then the integral of 2x with respect to x is going to be x squared. So that gives me that first term. And then integrating minus e to the minus xy y sine z with respect to x. This is the part that when I saw it in class was kind of throwing everyone off. So let's kind of take it like one step at a time. Minus y sine z, all that stuff is constant with respect to x. So we can kind of ignore it. And then all we need to think about right now is integrating e to the minus xy with respect to x. The other thing we know is that we integrate e and it always maintains the same argument. So we still get e to minus xy in our answer. But we always divide by whatever constant you have inside your e. So like the integral of e to the 2x gives you e to the 2x over 2, for example. So in this case, you've got minus xy up there, and you're integrating with respect to x. So that means you have to divide by minus y. Oh no, I needed that. Okay. And you might see right now that that minus y and minus y is going to cancel out. What we're going to have is x squared z cubed plus sine z e to the minus xy plus that potential unknown constant c1, which is a function of x and y and z. But I did not give myself enough space for that. So let's just scooch everything on over. So that's something that could depend on y and z, and so wouldn't appear in the derivative with respect to x and antiderivative. All right, next up, we're integrating the second component, the j hat component, with respect to y. This again has that messy looking integral in it. But minus x sine z is a constant as far as y is concerned, and then we're just integrating e to minus xy with respect to x. So that's going to give us, again, that e to minus, we're integrating with respect to y. That e to minus xy, and then divide by the constant in the exponent. The minus x is what's multiplied by y, so that's the part we divide by here. And again, that minus x is going to cancel out with that minus x in the denominator, and we're just going to be left with sine z e to minus xy plus potentially some unknown constant that depends only on x and z. And then integrating that last component, we've got 3x squared z squared. So x squared is a constant as far as z is concerned, but then 3z squared is going to integrate to z cubed, or 3z cubed divided by 3, which just gives us that z cubed. And then this is the part where I have to use the integral of that trig function. So integrating e to minus xy cosine of z. E to minus xy is a constant as far as z is concerned. There's no z in that exponential. And then integrating cosine of z, I Googled for us earlier, is just going to give us sine of z. And then there might be an unknown constant, c3, that depends only on y and x. And so we wouldn't have seen it doing this part of the problem. I don't like how crammed that is, so I'm just moving this down a little, give it some breathing room. There we go. Okay, so this was the tougher integral of every problem we've done so far, but now we just have to go through and pick the terms that go into our f. So we start at the top and we grab everything we found. So I've got x squared z cubed plus sine of z e to minus xy. And then I go down to my second integral and I sort of ignore anything that I already found. So the sine z e to minus xy already exists in my f, so I don't count it again. And then there's nothing else to add, so I'm done there. And then I go down to my third integral, and again I ignore anything I already found, but I already found x squared z cubed, and I already found e to minus xy sine z. So there's nothing new to add, and this is my complete answer for f. Real quick, I want to take a second and note, since f is exactly the same as my answer when I integrate with respect to x and my answer when I integrate with respect to y, I actually know at this point that c1 and c3 are both 0, which is the same thing I've had on the other problems I did up to this point. But, kind of worth noting, is that c2 is that term that we miss when we integrate with respect to y. So it's going to be that x squared z cubed. That has only x's and z's in it, and so when we take the j hat component, the derivative with respect to y, and integrate with respect to y, we can't recover that x squared z cubed. So that's why this middle one didn't look exactly like f, while the other two did look exactly like f. That's not something that, like, at the end of a problem you need to tell me what those c's were. I'm just pointing that out to you so you kind of understand why we always integrate with respect to all three variables, because there's always the potential, if you pick one variable, that you'll miss terms like this that don't depend on that variable. And then if we wanted to, we could also verify that this potential function f worked by calculating grad f. But I'm not going to do that. because I did it on the last two problems, and it'll be even longer on this one because of how complicated those derivatives are. But I guess I have the time for it. I'm going to finish the problem first, that way anyone who really wants to get to the answer can have it, and then at the end we'll go back and check that. But returning back to the request we had for this problem, so far we did this. We found a scalar potential function, and now we're trying to evaluate the line integral over any path that connects A to B. So that B is our endpoint and that A is our starting point. Oops. And that starting point is A equal to 1, 0, minus 1. And at this point, all I have to do is plug those points into my little f and then evaluate it. So, at the end point, x is 0. So I've got 0 squared, z cubed, z is 1. And then e to minus x is 0 and y is minus 1. And then at my starting point, x is 1, so that's going to be 1 squared. Z is minus 1, so that's times minus 1 cubed for that x squared z cubed. Plus sign of minus 1, because that's what z is. E to minus x is 1 and y is 0. So that term is 0. The argument inside the exponentials is 0. 1 squared is 1, negative 1 cubed is negative 1, because negative 1 times negative 1 is positive 1, times another negative 1 is negative 1. Sign of minus 1, and again we've got e to 0. E to 0 is 1, so what we've got is sine of 1 times 1 minus negative 1 plus sine of minus 1. So that's sine of 1 plus 1 minus sine of minus 1. And maybe those signs cancel out. I can never remember if it's the sine or the cosine, where like the minuses are the same or different. But I'm just going to leave it because WebWork can't simplify it for me. And my f, I said, was x squared z cubed plus sine of z. I don't know if it cares about that red line there. E to the minus xy. It did not care about that squiggle line that my computer didn't like. It detected multiplication. So that's the answer for this problem. Now I'm going to go back and verify this thing because I've got the extra time to do it. And you all might care. But since there's so many terms, I'm actually going to take my 3 derivatives and then plug them in. So the derivative with respect to x of x squared z cubed, x squared gets me 2x, and z cubed is a constant, so it stays there. And then when I take the derivative of sine z e to the minus xy, sine of z is a constant as far as x is concerned, so it stays. And when I take derivatives of exponentials, their argument is unchanged, so that stays there. And then all I have to do is multiply by the rate inside the exponential. So if I have e to 2x, the derivative becomes 2e to 2x. So that's just going to multiply out front a minus y. That's the stuff that's multiplied by the x here. looking at my derivative with respect to y, that first term, x squared z cubed, has no y in it, so the derivative of it is 0. And so sort of that's the reason why it creates this c2 term that only depends on x and z, because there's something in f that goes away when we take the derivative with respect to y. And then the second term, sine z, stays there because it's a constant as far as y is concerned. Eta minus xy stays there because it's an exponential, it's unchanged, except that we have to multiply by the rate inside. That's that minus x. So we're just going to get minus x sine z eta minus xy. And then taking derivatives of the third component, x squared is unchanged, it's a constant, but then the derivative of z cubed becomes 3z squared. And then since the integral of cosine is sine, I know that taking a derivative of sine doesn't throw a negative. So the derivative of sine z is cosine z. And then eta minus xy is a constant as far as z is concerned. So it just stays there. Sort of like if I had 2 sine z, it would take a derivative and become 2 cosine z. So my grad f is going to contain all those components, but as I write it, I'm going to rearrange it so it looks exactly like our f. So 2xz cubed minus, I'm just going to switch the order inside this term, eta minus xy times y times sine of z. All I did was rearrange, it didn't change anything about it. And then I've got minus x eta minus x, oops, kind of off the mark there, xy sine of z in my fy. And then I've got 3x squared z squared plus eta minus xy cosine of z. Again, just swapping the order of where that exponent went. And then if you look over here at web work, I've rearranged our answer so that it does perfectly match it. So we know that we did find the correct potential function. When we take the gradient, we end up back at the capital F we were given, which is what we want to happen with this type of problem. But again, that's not necessary to finish the problem. It's just sort of helping you hopefully understand how we arrive at these potential functions a little bit more by seeing it in reverse, because this calculating a gradient thing should be more familiar to you. We did it earlier in class. So those are all the question requests that we had. So I'm going to go ahead and stop recording and get this posted so that you all can see the answer.